Hi everyone. By the end of this video, you should be able to graph log functions. In order to figure out how to do that, we're going to start by graphing what you already know, which is an exponential function. And as we know, a log is the inverse of an exponential. So let's say I have the graph of f of x equals 2 to the x. This should look somewhat familiar. So if I graph that, just making a little table, plug in some values, like let's say plug in -2, the output would be 1/4, -1 would be 1/2, 0 would be 1, 1 would be 2, and 2 would be 4. So you can kind of see what's going on here. If you want to go a little further, if you did like 4, it would be 2 to the 4th, which would be 16. So you see it start to grow a little bit more there. So graphing that, it's going to look something like this. Here's your y-intercept. At 1, you are at 2, but at 2, you are at 4, and at 4, you're like way up here. And then it's going to start approaching our asymptote at the x-axis. So we should know how to graph this. This is an exponential function. The reason I'm graphing this is to figure out what a log looks like. So we've already learned that a log is the inverse of an exponential. So with that in mind, if I want to graph the inverse, I would just have to switch the inputs and the outputs. So f inverse of x would be 1/4 -2, 1/2 -1, 1 0, keep scrolling, 2 1, 4 2, and 16 4. Okay, so if I plot those, I'm at 1 0 is my x-intercept here. Then at, let's see, where x is 1/4, so here's about 1/4, I'd be at -2. If x is 1/2, I'd be at -1. Okay, so you see it's going to start approaching here. But then at 2, I'm at 1. And at 4, I'm at 2. And at 16, I'm going to be at 4. So like out here. So this function is actually going to approach the y-axis as an asymptote and shoot up towards positive infinity on the x-axis, which makes sense because we also learn that any inverse functions should be reflections over the origin or over the line y equals x, which if you folded this over that line I just drew, they would match up perfectly. So the reason I did this is to figure out what a log looks like. And this is the quote-unquote parent function of a log. And it's a parent function not because, we have a common base, the base can be anything, but because there's no transformations done to it. So I'm not adding anything to the x, I'm not adding anything to the outside, I'm not multiplying by a half or whatever. It's just the standard 2 to the x parent function, okay, which makes our blue graph here the inverse, which is the log. So in order to figure out what that function is, well, if I had f of x equals 2 to the x, if I want to find the inverse function, I would switch the x and the y. So I'm going to come over here, and I would get, well, f of x is y, so let's actually switch those. You'd get x equals 2 to the y. And that's what this graph is here. But in order to figure out, how is this a log? How is the log an inverse of an exponential? Well, a log solves for exponents. And in an exponential, you input exponents. Okay, so that's one way to think about how they're inverses. Okay, or if I wanted to get y alone, so I got this as a function, then in order to undo 2, I would have to take log with a base of 2 of both sides. So I'm even going to rewrite that. This is log base 2 of x, which equals log base 2 of 2 to the y. Okay, to figure out why this log base 2 cancels, I can go a little bit further with what I've learned. First of all, I'm going to use a log property and pull this y out to be a coefficient. So writing that over here, I'd have log base 2 of x equals y times log 2 of 2. Okay, so all I've done is taken this exponent and made a coefficient. Okay, now I'm trying to get y alone, and this log 2 of 2 is bothering the y. But if you think about log 2 of 2, what does that really equal to? So what this is asking is 2 to what power equals 2? And the answer would be 1. So log base 2 of 2 is just 1, and 1 times y is just y. So I can even get rid of that and say that the inverse function then is f inverse of x equals log 2 of x. And that's exactly what I graphed here. So this is the inverse function of 2 to the x. that is the graph of the inverse function. So that graph corresponds to this. And if you didn't want to find all the values for 2 to the x, you just wanted to graph a log, you can make a table of values for this function. You just might want to pick strategically. So let's just say I was like, just graph this log. There's no inverse, just graph log 2 of x. And I had xy chart here. What might I want to plug in for x? I might not want to plug in 3 because I don't know 2 to what power equals 3. That would be hard. But maybe I want to plug in 2. If I plugged in 2, it would really say 2 to what power is x? And the answer would be 1. Or maybe I want to plug in 4. 2 to what power is 4? The answer would be 2. Or maybe I'd want to skip ahead even more and go 8, because then 2 to what power is 8? It'd be 3. And then maybe I'd do 1. 2 to what power is 1? The answer would be 0. And of course I want to do some negative numbers. So what if I had a fourth? So 2 to what power is a fourth? It would have to be negative 2. And you would get the same graph I just graphed over here, but you don't have to do the inverse and then switch all the x's and y's. You can just graph it that way. So you should be able to evaluate this function to be able to graph it, to make a table, without looking at our exponential function. But you just kind of have to pick strategic values. Like, don't use 3 or 5. Use what works. Okay, I'm going to leave this one up here for you to try on your own. So graph it and graph the inverse. I might try making a table of the actual log and finding the log inverse instead of just switching the inputs and outputs. I just want to talk about transformations. So this is my parent function of a log. So it kind of looks like a reflected exponential. And I want to know what, actually I probably should say, the original function f of x was just f of x equals the natural log of x. So I want to know how each function will differ from the parent function. So if I throw a negative in front, or if I take negative x, or if I throw a 1/2 in front, or x plus 4. So one thing I want to reiterate, and that comes up in all of these math classes that you're going to take, is anytime you're transforming a function, all the transformations are relatively the same. It's just shifting that function. So like whatever I did, if I had negative x squared, the same thing I do if I have negative natural log of x. You're just shifting a different function. Or if I add x plus 4, it's going to shift this the same way it would shift x plus 4 squared. Right? So to write verbally, what would happen is I would take the natural log function and I would go left 4. And you can write that out yourself. So go from natural log of x and then move left 4. So I would go back 1, 2, 3, 4 and plot all those points. Okay? If I had negative natural log of x, that's like taking negative of my y's. So if I do negative y's, if I start up here, it would come down here. If I start up here, it would come down here, so on and so forth. So what that means is it would reflect over the x-axis. Reflect over x-axis. And I shouldn't even have to go over these. You should be able to do these on your own. So I guess with that said, I'm going to leave these for you. Write out what those would do, and also do this problem. So first I would find the inverse function of this, and then graph it like I did here. So actually practice evaluating logs. And I'm going to check and make sure that you have that done. So please do that on your own. Come to class with questions, and have a great night.